Alright, hi everyone, welcome to lecture 9. In our lecture 8, we talked about the production of X-ray. We gave an overview of X-ray, how X-ray is being produced. And in lecture 9, we're going to take a voyage to the realization of how the electrons are being produced. That is where we are going to do today. We are going to talk about the filament or the cathode. Now, cathode filament is made up of two parts. The first part is the filament, and the second part is the focusing cup. Now, a filament, let me show it. Now, this is the cathode. This is the cathode. Now, cathode is made up of the filament and the focusing cup. If we look at the cross section of this filament, this is how it will look like. Now, this filament has the cathode is composed of two filaments. We have shorter filament and longer filament. And the use of these filaments, the choice depends on the number of beams of electrons that we want to produce, and it's also informed by the type of focusing cup that is used. Now, the filament is made up of a material of high melting point, and the material that met this standard is still the tungsten that we use even in our anode target. Now, tungsten has the property of having high atomic number, making it to have a lot of electrons that can be released, and also it can be drawn into a wire, because when it's drawn into a wire, then it will kind of increase the surface area upon which the electrons are going to be produced, and it also have high melting point that makes it gives the capability to withstand its integrity even upon heating. Now, we have different types of material that can be used, but tungsten is preferred in this case because of the qualities that I've just mentioned. Now, when we come to focusing cup also is made up of a material that can be highly negative. That material must also have high atomic number, and the fact that it has high atomic number does not make it a good thermionic emission. It cannot emit electrons, but it has capability to produce high negative or high repulsive force that makes these electrons to be focused. Now, normally we have three types of focusing cup. Now, you can either have unbiased focusing cup. The current supply to the filament and the cup are shared. As you can see, we have the current supply to the filament and the filament here, and then the same supply supplies the cup. And in reality, this is kind of beam that is going to produce. As you can see, the cup is trying to focus the electrons. Now, the second type of focusing cup is the bias. We have unbiased, then we have biased. Now, the biased type of focusing cup, this is where the current supply of the cup is independent of the filament, and therefore you can increase the negativity of the cup, whereas not tampering with the electron production, or you can increase the electron production but not tampering with the negativity of the cup. Now, this one also leads us to this type of electrons being produced, and as you can see how they're being focused. If you wanted to focus it in a very small effective focal, then it is proper you use this, and this one also informs by the type of the the filament that is used. Now that we say that we have two types of filaments, we have a longer filament and a shorter filament. Now, which we just shown here, we have a longer one and a shorter one. Now we have the third type of the bias. So this is the grid bias. Now the grid bias, the cap is made so electronegative. It is so electronegative to the extent that it doesn't allow any electron to move out of the filament. The electrons are subdued at this point. They don't move out. And therefore there's nothing that is going to happen. There is no production of X-ray, particularly in this, because the electrons are not moving towards the target. They're being repelled down. So when you look at this one leads us to the realization that when you want to produce an electron, depending on the amount of electron that you want to produce, or depending on the type of filament that you want to use, you'll be able to acquire different beams. And it also informs us that now if we make the grid or the cap to be so electronegative to the extent that it does not allow some electrons to move, then we are rest assured that the electrons that that are going to reach the anode will be few, and even if they are few, then automatically the production of X-ray equivalently is going to be minimal. Now that you understand that the X-ray is just but 1% of the total energy, total kinetic energy is possessed by these electrons. So it's proper that we appreciate the fact that whenever we set to do a production, we must know which type of filament we're going to use and which type of grading system that we're going to use. Because if we use a wrong grading system, such as the grid bias, then automatically there will be no production of X-ray. It may think now that we don't even see these X-rays, these energies, we don't see them. They're just beams. Okay, the effects can be seen, but we cannot really see an X-ray. So you may be thinking that you want to produce an image, and the production of image is better because the detector will be there to detect. Now, in an event you are doing treatment in radiotherapy, then this is so dangerous because you may think that you have deposited some energy, whereas you grid all the energy and you grid all the electrons, and none has reached the target, and therefore there has been production of X-ray, which is expected to do the treatment. So the understanding of the biasing system is equivalently of great treasure, and we should really understand how to do the manipulation and understand which grid is supposed to be used at what point, and maybe understand the reason why it's being applied. Now that is the end of our lecture 8, that is lecture 9, and I welcome you all to our lecture 10, where we'll be discussing some other parts of the X-ray machine. Thank you very much, and see you in the next lecture.